Hi everybody, we are shifting into activity 2 here. So you'll need your book, formula sheet, calculator, and a pencil/highlighter. Either keep a running tally with that formula sheet, or you may want to start a new one for activity 2, similar to what I would have had you guys done in the classroom. Today, the reason we're shifting gears, and you might want to shift formula sheets, is we are actually shifting into geometric sequences today. So we're going to talk about what makes them so special and determining a common ratio. Now, way back when, week 1, last week, getting ready practice, earlier this week, we talked about these lovely 45, 45, 90s, but more importantly, 30, 60, 90 right triangles. And I want to highlight your knowledge about this and review this because we are going to use this principle today as we start with this lesson. So notice here we have Shelley's seashells, and we're making this lovely spiralized pattern on a polar grid. Now, I love that they put the math term here, polar grid. You don't need to know what a polar grid is, honestly, until Unit 5B. So you got some time. But notice this is just a different kind of grid. Like we have a coordinate plane. Here's our polar grid. So what you will see here is an initial lovely triangle, right triangle specifically. And what we know about this triangle is that it is going to be a 30, 60, 90 right triangle, because we see with this polar grid that we are headed out to the 30-degree marker. So we can indicate that this is in fact one of those special right triangles, and that the hypotenuse is 8 units long. Now back on the getting ready practice that we chatted about that this again is double the length of our shortest side, this hypotenuse, and then we know that the side across from the 60, that longer leg, is just the value of our short leg times the square root of 3. So if we move down here, we have the exact length of our hypotenuse is 8, which is also 8 if we approximate it. And that means as we draw in our next triangle here and around, another right triangle, another 30 degrees, aka 60, 90. This time that means the hypotenuse is the length of the former longer leg, so 4 square root 3, okay? And you're going to want to take the decimal approximation of that in your calculator as well, which I believe is about 6.93, okay? Well, same principle applies. If we divide this by 2 to get the side across from the 30, we get 2 square root 3. And then when we multiply by the square root of 3 to get the side across from the 60, reminder, 2 square root 3 times square root 3 is just 2 times 3, which is 6. So our next hypotenuse of our newly drawn in right triangle is 6. Which again approximated is 6. From there, divide that by 2 to get the length of our short sides, 3, and then multiply that by the square root of 3. Our next hypotenuse is 3 square root 3, which you could take the decimal approximation of. And then this is where things start to get a little ugly because we're going to start involving some fractions. So again, divide that by 2. We're going to just take that 3 square root 3, divide it by 2. And as we move through, 3 square root 3 divided by 2 times the square root of 3 is going to equate to be 3 times 3 divided by 2, aka 9/2. Okay? And you're possibly starting to see the pattern here, but otherwise try completing the rest of these on your own and just see how far we can get. Now, what you should have gotten if you finish this lovely spiral out, so we left off with the 9/2, but now we have 9 square root 3 divided by 4, 27/8, 27 square root 3 over 16 and 81 32nds, and then all those lovely decimal approximations. Now, excuse me, you're probably saying, Miss Sechuk, what does this have to do with anything? Well, we needed this sequence to be able to write in. So once we get all of these jotted down, we will see that our sequence here is that lovely top row. And the reason we want these decimal approximations is to be able to graph them, because while radicals are lovely for exact lengths, radicals and fractions are not as much fun to graph. So take a moment to graph. And we should see here that we have this lovely approximation here. And part 3 is asking us, are these lengths of the hypotenuses in Shelley's design forming an arithmetic sequence like we talked about in the first lessons? Why or why not? Well, the answer here is definitely no. And the reason being, these are not arithmetic for a variety of different potential reasons. One being there is not a constant difference. You may have said that it's not, not collinear as another way of putting this, not a linear graph, so non-collinear points, not creating that lovely straight line effect. Okay. But what this is actually, in fact, is an example of a geometric sequence. And instead of using the common difference with variable d, we're using a constant or common ratio r. And basically what has to happen each time in order for you to find the common ratio is, prior to this, when we talked about the common difference, we would subtract, two consecutive terms. And those consecutive terms would be like a2 minus a1, right? You subtracted two terms, a term and its preceding term. Here we are going to be dividing a term and its preceding term. So a2 over a1, or a6 divided by a5, or again using our lovely subscript notation, a sub n divided by its preceding term, the term before it, a sub n minus 1. Okay, so some very important vocab words to have there. So while arithmetic sequences are adding and subtracting, our common ratio geometric sequences are basically kind of think multiplication or division, although we usually only say multiply. Now, to test this theory out, let's go back to our lovely sequence from the last page, right? Our second term divided by our first term is going to be our value. Well, our second term was 4 square root 3. First term was 8, which simplifies to be the square root of 3 over 2. Now, if this matches, for instance, the third term divided by the second term, we would be able to see that these are in fact geometric. So if we take the third term, which was 6, and divide it by the second term, which was 4 square root 3, we can start simplifying here by rationalizing the top and the bottom. So remember, with rationalizing, multiply the top and the bottom by that square root 3. So we end up with 6 square root 3 over 4 times 3, which is 12. And then simplify. Again, these matched, so we have our common ratio. So that's our way to find r each time, is divide two consecutive terms. So up at the top of page 21 here, you'll see that there is, in fact, again, this kind of connects to this. There's a common ratio, of square root 3 over 2 between our consecutive terms. Right, so that's how we can identify if these are or are not geometric. Now, just like our arithmetic sequences. Okay. We also want to discuss with our geometric sequences an explicit formula to make our lives a little bit easier. With arithmetic sequences, we already kind of got a little head start with Desmos activity and notes where we were able to come up with those algebraic expressions, but we also found out a formula that's going to work each time as well. We want to do the same thing now with these geometric sequences. So notice here we have our lovely sequence from the last page, and we are going to fill in the charts for each term in our sequence. We're going to fill in the value here from before. So if I copied there, 9 halves, and then 9 square root 3 divided by 4. Okay. So what you're going to notice is they want us to write this as a product of the first term and the power of the ratio. Well, a reminder, our first term was 8. Let's look right above that. And our common ratio each time was the square root of 3 over 2. And we want to write these as a product. So notice 8 times the square root of 3 over 2 to the first power is going to have us equal 8. And in order to get 8 times the square root of 3 over 2 to equal 4/3, square root of 3 over 2 would have to be risen to the power of 1. And to get 8 times the square root of 3 over 2 to equal 6, the square root of 3 over 2 would have to be risen to the second power. Are you seeing a pattern? Well, hopefully what you are acknowledging here is that each of these, each time, to get the fifth term, we're now raising it to the fourth power. And to get the sixth term, we are now raising that common ratio to the fifth power. So each time, what seems to be happening is that to get our next term, we are taking 8 and our common ratio and raising it to the term before number, right? N minus 1, right? If we want n to be 6, we had to raise it to the 6 minus 1 power. So if you look on the last piece here, part C, which is on page 22, how now can we calculate a sub 11 directly so we don't have to draw 11 of those triangles? Well, plugging into kind of our new formula, if we generalize this a little bit, we're basically saying that we want the first term times our ratio to the n minus 1 power, which we will talk about a little bit more in the next lesson to begin. But we're going to take 8. We're going to take the square root of 3 over 2, and we're going to take it now to the 11 minus 1 power, which we can then press into the calculator and check. Sorry, should have had this loaded up beforehand. Taking a little coffee break here. So sorry. So 8 times the square root of 3 divided by 2 to the 10th power, right? Because 11 minus 1 is 10. We get a decimal here that we can turn into our lovely fraction of 243 over 128. Now, this makes sense as well. The second part, does this help confirm our answer? It kind of makes sense because if we go back to this pattern here, all of our odd numbered terms, 1, 3, 5, those were all the ones that were just fractions or whole numbers, and it was all of our even numbered terms, 2, 4, and 6, that had that radical 3 involved. So it makes sense that term number 11 is a fraction and doesn't have the square root of 3 over 2 involved. So we kind of see it starting to still fit our pattern overall. Okay. Now, we are going to get more into these lovely formulas at the beginning of lesson 2 as well. They kind of connect this back again, but if you want to get these written down now, I highly recommend the common ratio formula for sure, and this explicit geometric formula as well. And then we will move on and work with this more in lesson 2. Thanks, everyone.